Hello guys, my name is Bryce Turner, and today I will be going through my final project for CSCI-90, Cloud Services, Infrastructure, and Computing. My project is titled Building and Exploring the Z1 Financial Accounts Data Using AWS Neptune. I construct a graph using the financial accounts of the United States called the Z1. This data is published by the Board of Governors of the Federal Reserve System, and it tracks the flow of money through the economy. This data is currently published in tables without explicit interactions to each other, though I think this type of data lends itself to a graphical representation. In any transaction, there is always at least two individuals in a transaction, and they are exchanging at least one financial product. If we think of the individuals as vertices, the transaction as the edge between the individuals, and the financial product as an edge description, then voila, we have a graphical representation. However, the financial accounts is published as a set of CSV tables, each table representing the balance sheet of a given sector. There's a couple of other tables too, but generally this is what it does. These balance sheet tables contain the financial products for an entire sector, but not necessarily the other party in the transactions. Essentially, this data is just being currently published as a vertex with an edge. There are very good reasons to do this, but this project completes the relationship necessary. I associate that missing vertex with what is already listed on the balance sheet. There's a short video on my YouTube that I've already made, which you can access here. And then I'm making the long video right now, so I don't have the link. So what are we going to go through today? We just did the project description. Then I'll go through the materials that are included in the download. I'll show you what my S3 bucket looks like. I'll show you the IAM roles you need to set up. We can go through my AWS Glue notebook that I use to make the graph data, and then my AWS Neptune Jupyter Workbench notebook that I use to, well, I create the graph first, and then I explore that graph using Jupyter. Okay, so let's start with the raw data. This is what the raw data looks like. This is the F101 table, which I know is the household and nonprofit financial sector, but it's mostly just the households, what they hold. So we've got a date, and then we've got a financial relationship or financial transaction. I don't remember what this one is right now, but it's probably like household net worth or something like that. So we just have households and this transaction. And what I aim to do is I add this data dictionary, which normally comes pre-populated from Z1. So this 1001 is household net worth, personal income, okay? Now there's no natively external relationship for that. That's sort of self-referential. But if you look further down here at another one, household and nonprofits organizations, agency and GSE-backed securities assets held directly by individuals, in a brokerage account or something like that. That very clearly does have another side to that transaction, right? That is, those assets sitting on a household's balance sheet are the liability of the agency and government-sponsored enterprises. If we look here at this one, 30611, this is the Treasury securities. It's an asset on the household, but that shows up as a liability for Treasury. And so we can take the 101 table, and via this code here, we relate it to the F106 table. And I can show you a list of what the Z1 tables look like. So these are all the tables. We've got the F101 that we're looking at here, households and nonprofit orgs. What do we talk about? F106, that's the federal government. We've got some banks, life insurance, private pensions, bunch of financial type organizations, mutual funds, closed-end funds, ETFs, on and on and on. And then the one that I'll be exploring today is F33, the rest of the world. If we look at these, they all look exactly the same. They're all the rest of the world. We've got the series code and the date and sort of what they are. So I'm going to link all of these together using AWS. So let's look at my S3 bucket. So this is what my S3 bucket looks like. I've got this big bucket with a date. This is the release date for the Z1 data. If you click in here, this CSV folder contains all the CSVs that come from the Z1. This data dictionary is all the data dictionaries that come with package Z1. And then the rest I make. So this data dictionary for graph, this is a single one because I'm just looking at the household tables here. But to fully flesh this out, you need an economist and everything to sort of pull through all the relationships. But this is the start. These vertex files, which is just one vertex file, that is just that vertex file. Well, it's a little screwed up when you download it, but it is the ID, which is the F101. It's got a label, which is the same. It's got a name, which here is domestic non-financial, and it's got a table type, which is a flow. Yeah, something about this is funky. It doesn't like, but it's got all this information there. Don't save that. Don't save that. Okay, so this is what all the raw data looks like. Then our end goal here is to make an edge file. So that way we can upload that into Neptune and do our exploring. But in order to do that, we need two IM roles. I've got a bunch of them. We need this AWS service role. Now, I created this in AWS Glue, just with the default FOS, but I actually needed to add a couple more permissions. I needed to let it delete objects in this flow of funds bucket, so that way I could do an overwrite. I also explored Code Whisperer, and I thought it was mediocre. Most of the time got in the way and was not very useful, but it is technically here, and it was interesting to explore with, but I would not recommend it quite yet. But really what we need here is this S3 stuff. Allow Glue to delete objects in S3. So that's all we need to get started with Glue. Now, I wrote all of this logic myself using PySpark. We'll talk about it in a bit, but in order to get data into Neptune, the data has to end up in S3. And there were a couple of complex things that I had to do in here that doing with the point and click and draw approach in Glue was not very friendly. And I know some PySpark, so I just did it this way. There's no reason that you couldn't do it the other way, more complicated way, but this is it. So what are we doing here? We read a data dictionary, that data dictionary that I talked about using Spark. So we load it in, it's a tab delimited, even though it's labeled as CSV, it is tab delimited. And then we do a couple of manipulations. So, we filter where there's no out table, because as I showed you before, not all of the series have like an out. That makes sense. We convert this out table to a list, which we'll use later, in instances where there's more than one potential table. We have to handle that case. We will extract some information about the name. This is the name of the table. And then we also get a label, which is basically just asset or liability. This sort of shows the direction that the money is flowing. And then we're just going to append the series code with a q, so that way it matches later. And this is what that will look like. So we've got a series code, we've got the out table in a list, series description, which is household and nonprofits, something. The line number in the actual table, this we're not going to use. The table number, which is F101, which we already know. Some notes, it's all in billions of dollars. We've got the name of the financial assets or liability that is being purchased. And we've got whether that's an asset or a liability. Then we're going to read this FOF data frame. I tried so many times. I have no idea why it was not recognizing these column names. And so I just have to manually rename it. And so this is what the data frame looks like. You know, we've got all these individual series. This is just for the most recent date. All these individual series stacked up, each with a value. And these are what we call flows. They're not levels. So this is as of in 2023 Q2, this series increased by this much, or you know, this series decreased by this much. So this is a change, which is why they call it a flow. As you can see, this data is wide, right? Each series has its own column. But in order to get it into a graph, we need it to be long. So we need each of these columns to become their own row. I do that by splitting the data down. You collect it, put it in a dictionary, and then you append this series code equals series and value equals value. And then you put that in the PySpark row. I guess it's Spark row. And then once you have this list of edges, you just append it all together. So now we've got a series code, which is this, and we've got a value, which is this. And then we're going to stick that on to this data dictionary from above. The only last thing we have to do is we have to explode the data. So that way, well, first we join as above, as I just said, and then we have to explode the data. So that way, for series with more than one out table, we evenly split that value. So we'll expand it out. We will convert value. We'll we'll divide value by the number of out tables for that series, and we'll round it to 0 just to make it easy because we're talking in trillions of dollars. We will add the from, so all the from for each file is the same, so we can just add it as a literal. We'll give it a new ID, which is the series code, and then the column 2. So these series are unique for the from table. So FA1530330005 only shows up with F1 on F101. And then this is what the final data looks like. So we've got an ID, we've got ID from to label, we've got the value, which is a double, and we've got the name, which is a string. This is a very specific format with all these names and tildes and everything. So this is all perfectly proscribed to match the graph. The graph has a bulk loader that can read a number of different things, but I'm going to be using this format, which is based on the Gremlin graph query language. And then once all that's done, I write that back into my edge file, which is here, edge files. So this is a PySpark data frame. I'm not going too much into why. The way that when PySpark writes data out, it doesn't actually have all the data in one place. So the file you give it is actually a directory with, in this case, there's only one partition of data. And I didn't bother zipping it. You could zip it and put it as Parquet and whatever you want. Well, actually, you can't do Parquet, but you could take it and zip this down to make it even smaller. But so this is the full file URL for that CSV. The nice thing is that when we get to Neptune, Neptune will let you read in data from a directory, just like this. So all we have to do, all that we would need to do is give it this URI, which we can see here. We would just need to give it this URI, and it will read all the files underneath it, which in this case is 1 because we're doing a small amount of data. But if you were doing a massive amount of data, you'd have multiple files in here, and you could just pass that there. Okay, so that is my glue. I also tried to interact with Neptune programmatically this way, but it is kind of a pain because Glue does not natively sit in your VPC, and Neptune will only communicate with items in your VPC. I think I misconfigured something, but I gave up and I just, did the Neptune way. Okay, so now we have this data right here, ready to go. So now let's talk about Neptune. What is Neptune actually? Neptune actually is a cluster of computers building a graph. So I already have this one running, but to create a new one, you would go to clusters, create a database. I use provisioned just because I knew I was going to run it and then I'd stop and shut it down. But they do have serverless options here as well. I did dev and testing, which basically just gives it one AZ. And then I left the rest as default. This is how you would configure the notebook. You can add a new notebook. So for this one, I named it FOF, but you could name it FOF2 or whatever you want. Yep, and it creates a new IAM role and everything and associates it with that notebook. Great. You could click create. I'm not going to leave because I already had this guy running. So we click in here. This is all the information. We have an endpoint, which is a writer. We have an endpoint, which is a reader. If we were from inside the VPC, you can, ping off this and communicate with the bulk loader that way. The one thing you do have to do is you do have to associate this Neptune bulk loader role with the cluster. This bulk loader role basically just gives Neptune rights to read from S3, which we're going to need to do right now. So once you've got your cluster up, you can click on notebooks. You'll go see that notebook you made. You can go in here, sort of see it. There's really not much to see here. But what you can do is you can go to Actions and open Jupyter, which I've already got open. This brings you to a Jupyter instance. And I've got this, it's got a bunch of examples and everything, but I've got this working with the FOF graph. For the short video, I do a quick description here, create an AWS glue. But here we're going to talk about the AWS Neptune bulk loader. This AWS Neptune bulk loader lets you load in a variety of data formats, but they are sort of prescribed. And the way that that actually works is that it assumes an IAM role to read from S3, and you have to construct the IAM role, which we just talked about, and pass that into the bulk loader. In a production ETL, you could trigger this at the end of your ETL run, that AWS Glue run, but I didn't. I just did it this way. And the way that you interact with the graph is you use this query language called Gremlin. Neptune and this Neptune Workbench actually supports a variety of graph query languages like OpenCipher, or I think it even supports SparkQL, but I use Gremlin. So the first thing we need to do is we drop. So we go to our graph, which is g.v. This lists all the vertices, and then we drop it. And then basically you're always like moving throughout the graph. So you have to pass this iterate command, and then you say g, find all the edges, and then you drop that out. So now we have a totally blank, empty graph that we can run with. And so they also support this magic command called load, which is just lets you hit their endpoint to link that data. So the first thing we load into our graph is this vertex file, which I already made. I'm not going to run this whole thing again, but you click run like this. It pops up this little nice GUI for you. You pass it in the vertex files that you want to read into your graph. So we could do this. And then you have to pass it that bulk loader role that Neptune is going to assume when it tries to access this file, and you put it here in this load ARN. You have a couple of other options. You just have to make sure this region matches. So you have to make sure that the data here This bucket flow of is in the right region. Yeah, you have to make sure that it's in the right region. Where are we? Vertex files here. Here. Yep, it's in this AWS region. Even though S3 is global, recall that an individual file is sitting somewhere. And for Neptune, it has to be in your region. Yep, so that's the region. There's like a fail mode where will it skip misaligned records or will it will misaligned records cause the whole job to fail? Yep. Pull that in, hit submit. In 5 seconds, you'll have a new graph, which I guess I can do. Submit 4. Boom. So now we have all the vertices loaded into our graph. Then we have to load the edges. Same deal. Hit submit. Boom, load complete. And now we can query our graph. So this is the graph with all the vertices with the label F101. And we can, use this command value map to see what's actually in there. So for the vertex F10 labeled F101, or with an ID of F101, we've got a table name of flow, a table type of flow, which we talked about before, and we've got the table name, which is households and nonprofit organizations. Now, let's say you wanted to query all the liabilities. We can query V, and then we get these out edges that are called liabilities, which is what we made over here. So this is asset. In here, we're querying liability, and we see this path. So we go from V vertice F101, then we go to edge labeled with the series name in the out table, and we've got F101 has a liability to F110. And then we've got another one here with a different series to F110. These are probably banks. Then there are also some visualization options, so it lets you visualize the graph. And what I wanted to do is I wanted to explore all the ways that US households are directly related to the rest of the world. So we do, get all the vertices, because in this instance, we just have F101 in here. We look for all the out edges that are assets, and then we look at all the vertices. It's called in V, right? Because the edge goes from where you are, it goes out an edge into a new vertex. And so that's this. And then we're filtering where this in vertex has a table name called rest of the world. The way it pulls through information is it looks at this path. So you're always traversing through the graph. And so we get this path. And then we deconstruct that path into these values. So we got a table name, which is a table name. We've got the name, which is the name of the financial instrument. So, total mortgage. And then we've got what's the in vertex here, which is the rest of the world. And so if we look at this graph here, we can see, so the households have total mortgages. And if we click here, you can see the total mortgage. And then I think if we go here, yep, we'll get the values associated. And so we'll click here, go there, and we can see that they bought fewer mortgages, 256 fewer mortgages this year than they did last year from the rest of the world. Or we can click here. Oh, sorry, wrong thing. So this is down $732 billion in mortgages from last year. Loans are up by 506, so there's more loans this quarter than last quarter. And this is a gigantic number. that's 133 trillion, because this is all in billion, something like that. So yeah, so this was my final project. I spent a lot of time in AWS Glue trying to manipulate this data to get it all together, and then a lot of time in Neptune's Workbench to sort of build these, traverse through this graph, and come up with a quick exploration. Thank you.